This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development.
This week, I mean, for those who don't know, Ben was really considered one of the founders of the whole field of HCI. He was doing work in the area before it got labeled. He was involved in organizing the first HCI conference. He wrote what has widely been used as the main textbook for the field. Plus, he's had a series of research programs at University of Maryland over the years, and it's one of the main centers. So he's a very central figure in HCI and well worth hearing. As is Rob Miller, who is not quite as central a figure as Ben, but equally well worth hearing. From MIT CSAIL, which is the Computer Science and AI Laboratory. We've had a lot of speakers over time from the Media Lab, which is sort of a different cut at things. And Rob's work is in that sort of borderline between HCI and software engineering, in that he's really interested in the question of how do you get people to easily produce programs without needing the kind of sophisticated engineering tools that professionals use. And this is what we call Scott Clemmer here has a research in a similar vein, which is the so-called long tail of people who would like to be able to do things more than just read what's on the computer. But they're not going to go to CS graduate school to do it. With that?
Okay. Thank you, Terry. I'm going to talk about a couple of the systems that we've built over the past few years in the area of end-user programming, particularly for the web. But my work sits at the intersection of lots of fields, not just HCI and software engineering, but also artificial intelligence and, in fact, computer security. So we'll have an example today of a problem and a solution that we've done in the area of building more usable solutions to security problems as well. So you'll see an example of that. And this work couldn't have been done without the help of a lot of students. This was master's work of Michael Bolin and Greg Little and Eric Lieberman, Darius Hupp, and a bunch of other students contributed to the things that I'm going to show today. So most of the credit for this hard work belongs to them. So first, to set the stage, the web is increasingly an application platform, and I'm sure that's not news to most of the people in this room. Many of the things that we used to do on the desktop, in desktop applications, have now moved to the web. You know, whether they're managing our email, managing our calendar, or using internet applications, all these kinds of things are happening on the web. And increasingly, as we spend more time using the web as the place where we do work, we increasingly want to customize these web applications so that we can do our work better, so that the applications we use are better suited to our own needs and the kinds of tasks that we need to do with them. So here's some kinds of customization that you might imagine doing on a website or a web application. And these sort of range from the simplest to the sort of most complicated, most sophisticated kinds of customization. So the simplest is probably a bookmark. A bookmark on the web is essentially a shortcut. You are grabbing a state of a website or an application that you want to be able to return to later without having to do all the steps that it took to get to it. So just creating a bookmark is an example of a customization of a website. A little more complicated are customizations that change the appearance of the website. For instance, simplifying a very complicated website to make it more appropriate to your needs. For example, I've built a version of YouTube for my 3-year-old that eliminates a lot of the features of YouTube that he doesn't need and would only get him into trouble if he clicked on them by accident. So we want to be able to simplify and also perhaps enhance, add features to websites in order to make them more suited to our task. The next step might be automating, so taking a sequence of steps that you do in a web application and making it into a macro or a script so that you can do that faster. And then sort of the holy grail of web customization is this idea of mashing up 2 or more web applications, gluing them together and making them work together to accomplish one of our tasks. So I'm going to show examples over the course of this talk of all of these kinds of customization, ranging from bookmarks to mashups that we've built. Now, the good thing about the web, compared to the desktop, is that it's sort of inherently open in ways that the desktop was not. So, for example, the display of a web application sitting in your browser is just HTML. And in fact, you can change the way it looks and appears and behaves inside your browser without the cooperation even of the website. I can change this Google homepage, and we'll see some examples of actually doing that. And it's open to that kind of change, despite the fact that the creator of the website didn't really intend for it to be open. You compare that with the desktop. The user interface of a desktop application is basically just pixels. You can't do much with those pixels. Similarly, the back end of a web application happens over these open protocols and open formats like HTTP and HTML and XML, which you can snoop on and change and automate and parse. And the back end of a desktop application didn't have these hooks. It was invisible. It was behind the the pixel appearance of the application, unless the developer intentionally provided an API. So the good thing in the web is that even when developers don't give us APIs, we can still do things to customize and automate applications. But it's not necessarily easy. And here are two barriers, two problems in this area that we've sort of focused on. The first one is invisible complexity. So even though we can change the appearance of Google in our web browser, there's a big difference between the simple user interface that Google presents to you. It's sort of it's been lauded as one of the simplest user interfaces out there. But you actually go under the covers and look at its HTML source. It's far more complicated. And if you have to program it, if you have to customize it down at that level, here's a line of JavaScript, for example, that clicks on the I'm feeling lucky button. In order to actually figure out how to write that line of JavaScript, you have to do a lot of reverse engineering of this complex underlying HTML. And that's a barrier, even for programmers, even for people who know HTML and know JavaScript. This is a complexity barrier that they have to overcome. So our approach is we want to just program against this, against the rendered user interface, the thing that we're already familiar with and that's already visible to us. So this is an example of the kind of this is an example of a command that you can write in our system that is not only easy to create, because you're just using keywords from the rendered view, from the user interface, but it's also easier to understand. Looking at a script that had this line in it, I would be able to much more easily understand what it does than a script that has that line in it. So that's the first problem. The second problem is the problem of syntax. And this is more general than just web programming, but it bites you pretty hard in web programming, because web programming is increasingly requires knowing and learning a collection of different syntaxes and different programming languages and different formalisms, and mastering all of them. So, for example, here's a sort of equivalent line of code that clicks on that I'm feeling lucky button and does it by using an XPath. So this is an XPath pattern that matches that button. So in order to actually do this, you have to learn some JavaScript. You have to learn this XPath formalism. And that's a barrier, particularly for end users, for non-programming users, people who haven't had any training in programming at all. But it's also actually a barrier for programmers as well, because you have to master more than just one programming language. So our approach to this is to think about just throwing away the syntax barrier. What can we do without having any syntax in our language at all? What if we just use keywords for the whole language instead of using a formal syntax? So we'll see some examples of how you can use that in real applications and real programming systems. And the second piece of this, in fact, will be, rather than writing the program, you'll demonstrate it. So this is often called programming by example or programming by demonstration, where you actually specify the automation that you want to happen by clicking on things and filling in forms. So we'll see some systems that do that. So that's a high-level view of what I'll be talking about. Here's sort of a visual outline of where we're going. I'm going to show you a bunch of systems that we've built in this area. We'll gradually fill in this picture here. Most of these systems are in the web domain, so they're built on top of the Firefox web browser. But I'll also show you at the end an example where we've taken this idea of programming with keywords, programming without syntax, and applied it to Java programming. So that will be a system that's built inside the Eclipse integrated development environment for Java. So diving in, the first thing I want to show you is Chickenfoot, which is our programming system for doing these kinds of web automation and customization problems. And the key idea of Chickenfoot is that users shouldn't have to look at the HTML source code in order to automate and customize a website. And the way we do that is with keyword patterns that match keywords in the text, in the actual rendered view of the page, in order to identify what it is that you want to interact with. For instance, the click feeling lucky command clicks on the best match to the keywords feeling lucky. So let me actually give you a demo of Chickenfoot. This is Firefox showing the Google homepage, and the sidebar on the left is Chickenfoot. And this is an editor where I can enter Chickenfoot scripts. And what I'm going to demonstrate for you now is a script that searches Google for people's faces, so that I can type in, let's say, Bill Gates, and be able to come up with a picture of Bill Gates' face. You'll see later in the talk why I want to be able to do this, but for now, just assume this is something that I do frequently. So I want a shortcut. I want to be able to automate this task. So the first step in this task from the Google homepage is to first get into to image searching mode. So I'll run a command here, click images. And what happened was it searched for the best button or hyperlink on the page that was the best match for this keyword that I put as the argument to the click command. And so similarly, I can say click advanced, and that's going to click the advanced image search link over on the right. And then on the advanced image search form, I can say I want you to pick the faces radio button, and the best match for that is this down here. And now finally, I want to fill in a search query. So I want to put some Bill Gates, for example, into this text box here. And so I need some keywords that will be able to identify that text box. So I'll pull some keywords out of its caption here and just say, let's say I want you to enter into the all words text box Bill Gates. And that will fill that in. And then finally, we'll click on the search button. So this little script essentially automated that sequence of actions that did a search for Bill Gates' face. That bit that I just showed you is the kernel of this larger script. So what I just showed you is this sequence of commands right here. This larger script, which is going to customize Google's homepage. Let me get back to Google's homepage. Oops, it already has the customization in it. Let me just turn that off so you can see what Google's homepage looks like without it.
For those who don't know, the picture there is different, not because of something that he did.
Yes,
because
this is Google
is today
Google's
celebrating
branding
the invention of the laser.
Oh, really? Is that what it means?
Yeah, it's the invention of the laser.
Cool. Yeah, I didn't customize that. So what I want to do is be able to make this a command that is always available to me when I'm looking at the Google homepage. So what this script does is it takes that kernel that I just showed you how to do and abstracts it, so it's not always searching for Bill Gates anymore, but instead is determining the person I want to search for by finding this text box on the homepage and extracting the whatever I've typed into that. And then wraps that whole behavior up into a function, which in turn is the handler of a button, and then that button is inserted on the page, again using a keyword pattern. So saying I want to put that after the I'm feeling lucky button, so that if I run this script, what I get is a new button on the page that's inserted in there as if Google had provided it for me, and that when I click on it will run that function and go through and do the search for Uma Thurman's faces. And I can essentially attach that script as a trigger that fires whenever I visit google.com so that it will essentially always be available to me. So I've done two things here with this example. I've customized Google's appearance. I've added a new button to the Google homepage. So I've customized the way Google works. And I've automated it. So clicking on that button runs an automatic script that retrieves those faces. So both of these things are important.
Hey, Rob.
Question?
At some point, I imagine you'll get to it, but I thought I'd flag it out of curiosity, is there's been a lot of hype around mashups on the web. And it's clear that some kinds of customizations are enormously useful. And other kinds are things that programmers invented because it was fun to build infrastructure for. And I mean, from having seen Chickenfoot and your other tools before, there's some really slick stuff you can do. And I'm wondering if you've started to build a theory of these are the kinds of customizations that end users find most valuable. And the community should focus on A and not B. You don't have to answer it now, but just at some point in the talk, if we get to hand-waving about that, I'd be really interested.
Maybe I'll save it for the end.
Great.
Just in case we don't have time. But it is a very good question. Let me show you a little larger example here. This is, let's see if I can actually get to it. This is our bug database for Chickenfoot, if it ever comes up. And this is actually an open source bug database that we're using. So we actually have the source code for this. It's written in PHP. And one of the things that I frequently do with this bug list is to assign bugs to people to fix or to change severities and priorities. And actually doing that in this interface is very painful because I have to click on each bug, go into a view of the bug, and then click in to edit the bug, and then choose the severity that I wanted, and then back up to the whole summary list. What I really want to be able to do is just change it in place, be able to just directly manipulate this list. Now, I could have dived into the open source, dived into the PHP, and tried to understand how to add that to this bug database, add that behavior. But that would require learning a lot more interfaces and a lot more of the system than I wanted to learn. Right? Whereas I already knew how to use the user interface of this thing. I already knew how to click into the bugs in order to actually change the severity. So what you've just seen me do, I clicked on a link there that actually fired a Chickenfoot script that automated the interface in order to pull out the drop-down lists for each of these properties, severity, priority, status, assigned to, and so forth, so that it could embed them in this page. And when I change one, it will go in, again, automating the interface, click into that bug and change its severity and essentially automate the tasks that I would have done manually. So doing that in Chickenfoot took less than an hour to do because I was using interfaces that were already familiar to me. I was programming against the user interface of the bug database rather than diving into the source code of the bug database. So even though the source code was available to me, that was a barrier that that was too much for me to want to surmount. Okay, I hope that gives you some idea of what we can do with Chickenfoot. One of the evaluations we did on this work was to see how well keyword patterns actually work as a method for identifying page components. So we did a little evaluation in which we found text boxes on the web with various different kinds of labels in order to sort of stress this approach of matching text boxes by their label captions. So some of them were sort of clearly labeled with textual captions like these top two, and some of them had no clear caption around them at all. And one of the interesting results of this is, first of all, the system was largely successful. So users were giving keyword commands, keyword patterns that were correctly identifying the text box on the web page, except down here in this case. So it's interesting to see where the system goes wrong. And this was a case that we chose because it was sort of intentionally ambiguous. There were two text boxes on the page that had the same label right next to them, this middle initial label. And users actually used two different kinds of disambiguation strategies to identify these things with keywords. One was counting. So this was a typical kind of expression that we'd see. And our system at that time actually didn't support counting, but it does now. The other was to use sort of more contextual keywords, such as the title of the section or the subform that text box was in. We don't currently support this, and it's a little harder to see how to support this without making the system sort of increasingly ambiguous in other situations. I want to show you now a slightly larger example of using Chickenfoot to do web automation and customization. And this is where we're going to pull in the other part of my group's work on computer security. And let me just frame the problem for you. The problem is sending email to the wrong people. And we've collected a couple of anecdotes about this. The first one appeared in the Wall Street Journal a couple of years ago, where somebody was replying to an email from their health insurer and asking whether such and such a very personal medical problem would be covered. But they didn't realize that they had actually pushed reply all to a message that was sent to the whole company. So their reply went out to the whole company as well. This has happened at MIT. A teaching assistant once wrote an exam and thought that he was emailing it to the professor to be checked. Where do you think he actually sent it? To the class. Exactly right. So they had to throw it away and rewrite it. And this is a case that actually appeared just a couple of months ago. A lawyer for the drug company Eli Lilly thought he was sending mail to one of his fellow lawyers talking about the case. But in fact, it went to a New York Times reporter who happened to have the same last name. So it was probably a sort of an autocomplete error. And it ended up on the New York Times front page. So this is really a security problem. And in fact, I'd argue it's an access control problem. Most of the file sharing that actually happens outside of an organization happens through attachments on email. So if you send it to the wrong people, that's like specifying the file permissions for that file wrong. And there are many ways it can happen in our mail clients. The consequences are usually just embarrassing, sometimes just annoying to the other people who got this message. But sometimes they're violations of privacy or security. And I would argue, even though this, the state of email infrastructure, the security of the email infrastructure is a disaster right now. Right? We have viruses and spam and phishing, and all of these things are due to the fact that we're not encrypting and signing our mail. But I would argue that even if tomorrow we all switch to secure email and we're all digitally signing and encrypting our mail, we would still make these errors. That lawyer for Eli Lilly would have sent beautifully signed an encrypted message that could only be read by the New York Times reporter that he sent it to. Right? So it's really a user interface problem. It's not something that's going to be solved by throwing cryptography at it. And here's our proposed solution to this problem. And we built this on top of Chickenfoot, so what I'm going to demo for you actually works in webmail clients. Here's a sort of a contrived example of a case where this might occur, where a faculty member at MIT is replying to an invitation to a department-wide retreat, and he says something not so complimentary about another faculty member, and doesn't realize that he's actually pushed reply all, so he's CCing all of the other faculty members in the department. We argue that he'd be less likely to send this message and make the mistake if this is what he actually saw in his email client, right? These are all the recipients of the message, and what you're doing is saying this to this whole crowd of people. And that there's a big difference. The reply all is probably the worst example of this case. There's a big difference between this big crowd of people and just a single face, a single person that you meant to be sending it to. And we've done some lab feasibility studies where subjects had only a brief glance at an email message like this, and there was sort of a big difference between, and asked whether they thought the email message was going to the right place or not. And there was an enormous difference between their ability to tell whether this was going to the right place and whether a mere textual message was going to the right place. So let me show you a demo of this in action. This is Gmail, and we have some Chickenfoot code running behind here that has added to the Gmail page this section here where faces will appear. And so that when I type in an email address in the to box, what actually happens is the system takes that email address and sends it as a query to a variety of image sources, including Google Images. So this is why I showed you how to do a face search in Google Images. This is one of the sources that we use for faces. We also use Facebook. You could also imagine hooking up a corporate or a university identity database to this so that you had a very high quality and accurate source of faces. But because it works automatically, we can actually type in a variety of email addresses in here. So Terry's, yours is Winograd at CS. And we'll come up with that. And your Clemmer?
SRK.
Ah, SRK.
I was curious. Clemmer's a secret alias. Let's see if that one actually works.
See what it does with SRK. So it's searching right now, actually. The other one was faster. Huh?
And of course, that mailing list, you can't get the names from.
Yes, so mailing lists are trickier. So for internal mailing lists, so for the MIT Mailman server, for example, we have a plugin that will go to the Mailman server and get the subscriber list for mailing lists that you are on. And that's how I got the members of the CSAIL faculty list there. For mailing lists that you do not have membership for, there is still a possibility of detecting that it's a mailing list, because many mailing lists give you headers and messages that say, I'm a mailing list. And if you can detect that this email address is a mailing list, but you can't find out its actual subscribers, you could still put up, say, 100 anonymous faces like that silhouette that you saw, which would help you to at least tell the difference between replying to one person and replying to a whole pile of people. Oops. Good. So that's sort of a bigger example of what you can do when you're automating and customizing websites. We didn't have to get Gmail's permission in order to do that. What's really a mashup between Gmail and a variety of other sources like Google Images and Facebook and Mailman. Okay, so I've shown you a couple of examples of things in the web. Let me turn to now the second barrier that we were concerned with. We looked at programming against the user interface. Second barrier, we're concerned with the problem of syntax. And Chickenfoot actually has this problem. So even though you can script the web without looking at the HTML of a web page, you still have to know JavaScript, because it's a JavaScript programming system, essentially. And we'd like to eliminate that. And so the idea is actually to take this notion of keyword patterns, which in a sense eliminate the syntax requirements of a pattern language. You just have to use keywords to identify something on a page. We're generalizing that notion to not just a pattern to identify a page component, but an entire command. So let's just use keywords to search the space of all script commands that would make sense at this point. This is actually an example from a prototype that we did in Microsoft Word, where you give some keywords, and the system generates a line of Visual Basic script that is the best match for those keywords and is syntactically and semantically correct. So here's some examples of the kinds of tolerance that a keyword command kind of language affords. So if you start with the original Chickenfoot JavaScript, which might look like this if you actually wrote it completely verbosely, you don't have to worry about punctuation anymore. So you throw away the parentheses and the quotes and the commas. You don't have to think hard about the order in which, say, the arguments go. So you don't have to know whether you had to name the text box before you put the data that you wanted to put in the text box. You can remove words and the system will infer them. So we left out the find command there. You can put in extraneous words that make it sound a little more like English. You can substitute synonyms rather than having to remember the exact name of the command. All of these things are valid keyword commands, including the original JavaScript, the way our interpreter works. So let me show you a quick demo of how this works. The previous two systems, actually, the Chickenfoot and the email system, are both available on the web as demos that you can try out. We haven't put this prototype that I'm showing you now up yet. So, for example, if I just type click advanced search, the system is now going to take those three keywords and find the best action it could take on that page that best matches those keywords. In this case, it was to click on that advanced search link. If I type something very concise like faces, that's going to, the best match for that is going to be this radio button here. And the most likely thing to do with that radio button is to click on it, is to select it, so that if I just run faces, it will simply select that. I'll show you filling in a text box. So we can, for example, take the all words text box and say we want to put Bill Gates in there. And the system will do that. Or I could write that a little more verbosely and say enter Bill Gates into the all words text box. And it will do the same thing. And then if I finally say click the search button, it will go through and click the search button. So, yep, question.
Basic question. What do you do about disambiguation? Suppose you had someone just type in enter, enter, enter. Supposing people just made the page like that.
Somebody could do that, but there are two ways to disambiguate. One is to enter into a dialogue with the user and ask, which of these interpretations did you actually mean? The system you're looking at right now doesn't do that, but a later one that we did in Java does. Right? Another is that the user can simply be a little more verbose. So in that kind of case, you know, if you said enter, enter, enter to me, I would say what, right? So there you'd probably want to actually add a little more extra verbiage to help the person you're talking to understand what you mean. And you can do that in this system as well. So you could put quotes around something that you wanted the system to treat as a parameter. And it would give a parameter interpretation to that. So if you want to say enter, enter in quotes into enter, then you'd be more likely to get what you want. Let's see, where are we here? OK, we did a little study of this as well. And it's a little tricky to do these kinds of studies because we wanted to really sort of test the learnability of this approach. And we didn't want to bias users to any particular syntax or any particular terms. So the instructions, in fact, said use only this command box to make what's in the red circles happen in your browser. In fact, the command box initially came up blank. So there were no examples of what they could actually type into that box. And the tasks that they had to do were simply described by screenshots with red circles on them, saying you had to make this happen and you had to make that happen. Here are the results. And the way to understand this chart is we had 9 subjects, so the columns of the chart are the subject's results, and the rows of the chart are each task, each red circle corresponds to a row. And the numbers in each cell refer to the number of attempts that the user made in order to try to get that task to work. And if they eventually succeeded, the cell is green. And if they eventually gave up, then the cell is gray. Okay? So the first thing to observe is that most of this is green. So 90% of these tasks actually eventually succeeded. It was some significant difference for programmers versus non-programmers, but non-programmers were still 84% of the time getting it right. And it would have been a drastically different number if we had actually had a JavaScript interpreter behind that thing, and they would have had to get JavaScript, essentially guess JavaScript syntax. I doubt we would have had anywhere near 84%. One of the interesting observations in this is that users actually didn't use verbs very much. They were just using the nouns, the parameters of the things that they wanted to act on. They weren't explicitly saying click. There was also a wide variety of syntax. So for instance, when you entered things into text boxes, sometimes the description of the text box came first, and sometimes the what it is that you wanted to type in came first. So that's these things sort of justified the decision to pay less attention to ordering in syntax. Question?
Is it correct to assume these were native English speakers?
These are all native English speakers, yes. It's also interesting to look at where this system went wrong. Synonyms turned out to be very important. So there was one task here where the system didn't have enough synonyms for, I think it was pick or select. And many of our users used a synonym that we hadn't put in the system. There was also a bug right here. This whole line is actually due to a bug that once we fixed it, the first attempt for all these users actually succeeded. The last one is due to a difference in user mental model from the way the system actually worked. So there was an assumption by the users that the system was modeling the keyboard focus. So once they had entered something into the first line of the street address, they could simply say, go to next line, and the system would know that they meant the next line. But in fact, the system didn't have any of that kind of model. It was taking each command as sort of a fresh command. So That is one issue with these kinds of systems, to make sure the user model and the system model actually synchronize. So this idea of sloppy programming and keyword commands has been picked up. So my student Greg Little, who did this work for his master's thesis, went to IBM Almaden as his summer intern, and while he was there, he developed the first version of Koala, which has since been released under the name of CoScriptor. And what CoScriptor is a web macro recorder, so that you can click on buttons and fill in forms, and CoScriptor will record the actions that you did. And the way it records it is as a script of commands, which are essentially keyword commands. And they're interpreted later, when you rerun the script, as keyword commands. And that allows users to edit this script sort of freely without having to worry about preserving a certain syntax. And we've also done some work on macro recording, on recording on the web as well, but we've done it for a different kind of problem, going back, in fact, to the first kind of customization problem I mentioned, which was bookmarking, being able to save a state in a web application. In the old days of the web, this was easy because a URL essentially captured all of the state that you would want to save. So you could just bookmark that URL. In modern sort of JavaScript-heavy dynamic websites, the URL no longer gets you back to the right place. Now, there are some sites that are aware of this. Google Maps, for example, for a long time has had the ability for you to get a URL that encodes the state of your current map. But there are hundreds of mashups based on Google Maps that don't provide this. And the reason is that it's a very hard thing to provide. It's not easy to recover this, to store all this state in a URL, so developers frequently don't do it. So our approach is to find a browser-side way that we can provide this functionality of bookmarking in sort of an arbitrary web application. And the way that we do it is to generalize the notion of a bookmark from simply a URL to a browsing script that consists of these keyword commands that click on links and operate forms and so forth, and allows you to play back those scripts in order to get back to a certain state in the web application. But in order to do this, simple web macro recording doesn't work anymore. And the reason is that by the time you want to make a bookmark, it's too late to push record. In the standard VCR metaphor, you have to push record first before you do the actions that you want to save, and then stop once you get to the point where you wanted to save it. But when you want to bookmark, you've already gotten there. You've already done your actions. And you probably didn't realize in advance that you needed to record it, so you didn't push that record button. So our approach is to do this retroactively. So the system is actually constantly recording your actions in a history as you're using the web. And whenever you want, you can ask the system to make a bookmark, which it does retroactively by scanning backwards through the history. And here's how it actually works. So here's an example of a history which has some URLs in it. This is where the browser went to a new page, but it also has some user actions like typing and filling in forms. And then we finally get down to this state at the bottom. It's actually the result of a flight search. And this is the state that we want to save. We want to capture a bookmark for that. So what the system needs to do is find a browsing script that starts with some URL. It starts with a goto command, and then has a sequence of instructions that will get you back to that page. And we want to find the shortest suffix of this history that will do that, so that we have a concise and fast to run bookmark. The way we do it is to start with the last URL in this history and test whether this is actually a bookmarkable URL. And the way we do it is to resubmit that URL, but resubmit it while simulating a fresh browsing session. We actually turn off cookies so that the request looks like it's coming from a different browser. And then we compare the page that we get back from that fresh request with the page that the user just saw. And if they're the same, then we say it's basically bookmarkable. You're going to get the same page back if you submit that URL again later. And if they're significantly different, then we say that it's not bookmarkable. So it turns out if you submit this URL, you get an error message back, or at least a substantially different page. So that's not bookmarkable. So the system steps back and checks the next URL and so forth, and keeps going back until it finally reaches a URL, which turns out to be the entry point of the Travelocity site, that is bookmarkable, that recovers the same page, or roughly the same page that, that you originally saw. And then the system turns that into a browsing script.
So how does it deal with cookie context there? That is, when I go to that page, if I have previously logged in, for example, it will automatically log me in, but if I haven't but the previous login could be 100 more interactions back.
Right. It may have to go back as far as that. It may have to go back as far as that login. So you may get a long browsing script as a result of this.
Which would include all the extraneous stuff you did in between.
Right. But then you can actually look at it, because it is readable by the user, and you can edit it. So you can remove a lot of that extraneous stuff if it turns out to be a very long browsing script. Yeah. That's certainly an issue. So one question with a lot of this work is, what happens when the web changes? Right? A browsing script in particular, a bookmark script in particular, could stop working if the website changes its form so that the particular actions that you did no longer work. So we did a little evaluation in which we took 25 websites and created bookmark scripts like you just saw for a task on each of these websites. And after 1 month, and checked again after 1 month and 4 month intervals whether the browsing script still works. And for the most part, we were getting about 80% success after 4 months. But the interesting thing to look at here again is where the system sort of fails. In Dell and Gateway, for example, these bookmarks actually customized laptops, and it turned out that even after 1 month, the base laptop that it was customizing was no longer available. So in fact, even if Dell and Gateway had given us a URL that would recover that customization, it would still have been broken because they would no longer be able to give us that state again. They don't sell that laptop anymore. So this is an example of an inevitable decay of a bookmark. These 4 cases here were cases where the website user interface changed in a way that broke the browsing script. For instance, MySpace introduced an interstitial ad that the browsing script didn't know how to deal with. Right? Although you can imagine just getting the system to automatically look for skip this ad links and click on them. Third case here was a case where our approach for testing bookmarkability of URLs was insufficient. So the Apple URL actually had a session identifier, a temporary session identifier, embedded in their URLs. So when we resubmitted that immediately in our sort of fresh browsing session, it looked like it was still alive. It looked like it was still bookmarkable. But an hour later or a day later, that session had expired, and so in fact the bookmark was now broken. So that's sort of a case where our model for testing whether a URL was bookmarkable was insufficient.
How do you deal with side effects? What if rerunning the page is charging your credit card or something?
Yes, great. Excellent point. Because a common case for using this kind of system might be, well, I want to bookmark the confirmation page for my airline reservation, or yes, that's a great point. One of the original visions of the web was that there should be this distinction between GET requests and POST requests, and that one of them would be idempotent, side effect free, and the other one would potentially cause a side effect. Unfortunately, the actual practice of the web does not respect that, and there's a whole ton of things out there that use POST that are side effect free. So there might have been something. There might have been sort of we might have hoped to actually get that information from HTTP, but it didn't work. The solution we've actually been exploring is much more heuristic. So looking for certain keywords in the buttons that you actually pressed, like confirm, which are indicative of possible side effects. So that if you run a script that has these kinds of keywords in it, it will warn you that there might be a side effect here. And you'll be able to inspect the script and say whether or not there's a side effect. That's another benefit of having this readable representation here. I mean, because it shows you, if you actually look at it, that, hey, it's actually entering my credit card number, and it's doing all these things to actually do the side effect. So it's important that this be viewable and readable by the human being, by the user. But they also have to look at it, and that's definitely an area that we want to be able to avoid, because it's a costly one. OK, so I've shown you a bunch of things in the web. I want to close by showing an example of where we've taken this idea of syntaxless programming over into Java, into the world of professional programmers, so to speak. And the way we've implemented it here, the user interface we've given to it is as a code completion mechanism, a way to generate code by giving a couple of keywords for the code that you want. So imagine I'm sitting here in this Java program that I'm writing, and I want to fill in the body of this loop with a line of code that will do this, read a line from the source stream and add it to this array that I've created. So I want to take some of the keywords from what I'm intending and just type those in as essentially a query over the space of all possible Java method calls that might make sense at this point in the code. So that when I press in Eclipse, we actually use control space. So we're just using the standard code completion interface in Eclipse. I get a list of possible matches to those keywords, arranged in a ranked order. And so in fact, the first one in this case is the right answer, and I press enter on that and add it to my code. So it's a way to generate Java code without having to put in all the punctuation or pay attention to even the ordering of parameters. We did a little evaluation of this using a corpus of open source Java projects. And what we did was to sample method calls, existing method calls in these projects. So we'd pull out a line of code like this and turn it into a plausible keyword query for that line of code. And the way we did that was to strip out punctuation and break up tokens into sort of individual words on the capitalization boundaries, and eliminate the capitalization, and then randomly reorder the resulting tokens. So just toss them in any order. And then see whether if we fed that into our search engine, we would actually get back as the first choice. So this is sort of the strongest measure of accuracy. It actually has to be the first choice on that n-best list. Whether we get back exactly the same line of code that was originally in that program. And here are the results. And these are actually arranged by grouped by the number of keywords that were in the resulting query. And first of all, most of these method calls, it turned out, had a relatively small number of keywords. And furthermore, the system was very effective when you gave it only a very small number of keywords. Overall, it achieved 90% accuracy, which I think is actually a very interesting thing, that the amount of information in the syntax of a Java method call, in the particular ordering of its arguments and in all the parentheses and commas that you have to put in just the right places, is so low that when you just throw it away and throw away even the ordering, 90% of the time you can get back the original line of code. So why are we typing it? It sort of begs the question. There's also this interesting effect here, which is that the longer the queries were, the more keywords there were, actually the worse the system did, which is really counterintuitive, because you'd think longer queries would be more precise. In fact, one of the things that's going on here is this longer keywords, longer queries, tend to refer to longer method calls, methods with more arguments in them. And methods with more arguments are more likely to actually have two arguments of the same type. And when that happens, the type constraints that are helping us figure out which keywords go where don't help at all in figuring out which of these, what order to assign the keywords to these parameters. Remember, we've randomly reordered. We've thrown away the order. So as a result, it's sort of a 50-50 shot whether the system's going to come up with the right ordering or not.
Programmer would have to do to enter it in your way versus enter it with something like autocomplete, where for a 5-part method call you might only type 5 characters?
Mm-hmm. No, we didn't actually do a sort of a keystroke level model or something like that. There is an issue with autocomplete, which is that you have to get the order right in autocomplete. You have to know which object you are going to call the method on, for instance. You have to know whether you're adding foos to bars or bars to foos, for example. If you don't know that order, then autocomplete isn't going to work.
But in your model, you have to know the spelling.
That's true. Well, I mean, we do some spell correction, but you do have to know the identifier as well. So there's sort of an issue with synonyms. There are no synonym support in this system yet, and autocomplete doesn't have that problem, right? Because you're recognizing what you want rather than trying to generate what you want. Yeah.
Mining Java docs where comments or terms of
Mining the documentation for other words that might be used, or using the documentation as a search, as one of the things that you're indexing is definitely a good idea. We haven't looked at that yet. We're only using what's available in the API type libraries.
What define made sense? I mean, what kind of things are you looking at? You said you found a piece of Java that made sense in that context.
Oh, made sense.
There are ways I can imagine that being defined.
What I mean by made sense is syntactically correct, is semantically correct, and uses would compile. So in this kind of context here, we're only using variables that are defined. For example, we're only using methods that are defined. That's what we mean by made sense. It's not a more semantic meaning of made sense. Although that would be an interesting direction too. And there have been other projects that have looked at things like that, where they're actually mining existing code to get a model of what makes sense.
So in studies we've done of programming, one of the things, I have a hunch, and this is mostly a hunch, that what's hard about contemporary programming is less, in a sense, composing individual lines, and more. Well, there are many things that are hard, of course, about contemporary programming, but the hardest one seems to be the programmer has in their head I'd like to get this stuff into the database, and it seems to be at the what is the programmatic, how do I implement this whole thing rather than how do I implement a particular line. How might you extend this approach to a bigger than one line chunk of programming?
We've started to think about that. One way that you might do it is to have a big source of examples that you can mine from, so that, and in fact, in a sense, that's what we're doing here, right? I mean, having a big pile of classes and methods that you're using and picking out pieces of them and gluing them together into a method call is sort of a small-scale version of what you might do if you had snippets of 5 lines or 10 lines or 5 classes or something like that that could match keywords. So the techniques you would use for it are probably different, and we haven't figured out what those are yet, but I think the interface might be similar. And we'd like to see how, sort of keyword searching can help with that. Okay, so I've shown you a bunch of examples that sort of target 2 problems or highlight 2 ideas in our work. One is programming against a user interface rather than against an API the developer has provided. And the other is using keywords rather than formal syntax. And I want to talk about some of the limitations and common questions about both of these approaches. So do you want to program against the user interface or against an API? Well, the UI is visible, right? It's something that you're already familiar with and that you don't have to go and find. It's right there in front of you. And it also definitely exists. So a lot of websites have not jumped on the Web 2.0 bandwagon of making all of their stuff available through web APIs. But they all have websites, and those websites can be automated and customized. But a programming interface is probably going to be faster, because it doesn't actually have to render the user interface in order to work. And it may be less likely to change. We looked at that bookmark robustness question, which website changes break the bookmarks. And it did happen, but APIs change as well. So Google's search API has recently been deprecated. Their original search API that they came out with a couple of years ago has been deprecated and is likely to go away, be turned off. but their user interface has not changed in 10 years, right? The I'm feeling lucky button is still there. And I would argue, I mean, I have a hypothesis that the rate of change of an interface, whether it's a user interface or an API, is going to be related to the number of dependencies on it. And there are dependencies on user interfaces. There are training and learning dependencies on user interfaces that make them resistant to change in similar ways that APIs become resistant to change. Backward compatibility affects human beings the same way it does programs. I've also observed from personal experience, I once had a meeting with a Yahoo executive, and 5 minutes before the meeting I realized all of my examples used Google. But I just changed the starting line of each of the scripts, so that instead of going to Google, I went to Yahoo, and it turned out most of the scripts still worked. Because there was so much consistency between the websites. Even though they were different in how their HTML was actually structured, the user level was similar enough that these keyword commands were robust. This other question, should we be using formal syntax or informal sloppy syntax for programming? I argue that keywords are easier to write and easier to read, and I think the history of information retrieval actually bears that out, that it moved away from Boolean algebra and into keyword searching for search engines, and that's been far more successful user interface. But formal syntax has a more precise meaning. You can give semantics to a formal syntax, and it's likely to be more expressive as well. I mean, we're not programming in English. We're programming in much more precisely defined syntaxes. And that's definitely an issue for these notions of keyword programming that I've shown you in these demos. They work largely because they're either in limited domains, like the web. There's only a few things that you can do on each web page. Or because we have all these other constraints that help the keyword search work. And Java method calls, for example, all these type constraints help us narrow down on the best match to your keywords that actually is syntactically and semantically correct. So it's clear you need these kinds of additional information in order to make up for the lack of precision of the keywords themselves. Another question is whether you can really trust a keyword program if you don't really have a clear semantics for what it means. And all these systems have shown you have a human in the loop, monitoring and making sure the thing doesn't go off the rails. And it's not clear. We don't know whether you can get away with that, whether you can it's actually an interesting research question whether you can get away with that. Another interesting research question is, should we stop at keywords? Should we try to go on to natural language? That's a natural language programming. That's a problem that's been revisited every decade or so for the last over the history of computer science. And this is sort of a different take on it. We're not using a natural language processing approaches. We're just using keyword matching approaches. So it's a lot simpler in that respect. So to conclude, I hope I've shown you some of the things you can do with web automation and with sloppy kinds of programming. And I'd be happy to take any questions. We're a little bit over a bit.
I was wondering if you'll be going the way of sort of James Allen plow system. So it's more of a natural language and demonstration web scraping. Any comments about that? It's the direction you'd be going towards.
Yeah, so James Allen has a very nice system that is a multimodal way to do a lot of these kinds of web data extraction and even a little bit of automation problems. So you can create macros in his system by talking to the computer. And what's nice about that is that it sort of gives you a meta channel in which to talk about what you're doing and why you're doing it instead of just doing it. And yeah, we're certainly interested in that. I've been talking to some of the speech people at MIT about putting speech on top of these kinds of systems, in particular so that these keywords that you're typing could perhaps be found in what you're uttering instead of having to force you to type them all the time. So yeah, it's definitely a great line of research. And James has a really nice demo on the web that I encourage you to check out if you haven't seen it. James Allen at University of Rochester, I think. Okay.
was wondering what the social aspects of Chickenfoot might be. So sharing scripts, like kind of visibility into what scripts have been written for the Google homepage, for example.
We don't have as much sharing as I would like there to be. We do have a wiki in which people post scripts. I know that we have over 10,000 users, but we certainly don't have 10,000 scripts on the website. And other systems like Koala and CoScriptor have actually been able to generate sort of a much richer collaboration between their users, because in fact they don't support anything other than collaboration. One of the interesting decisions in CoScriptor was that whenever you saved a script, it would always be saved on the wiki. You could mark scripts whether they would be public or private, but it was sort of much easier to put something up on the wiki. So we don't really have a clear idea of how people are sharing scripts in Chickenfoot. One common use for Chickenfoot, it turns out, is for website functionality testing by website developers. And those people don't really share their scripts with anybody because they're just sort of internal test suites that they're developing, that they're building. Yep.
One interesting social aspect could be the disambiguation. If somebody does figure out how to do the disambiguation, send that back over.
Yes, that would be a great idea. And be able to sort of record that, or even improve the keyword matching algorithm so that it does better on those kinds of sites, those kinds of page components in the future. Yeah. Collaborative web scraping is sort of another interesting area. You know, creating scrapers and being able to share them with other people.
I know this is a dumb question, but
why is it called Chickenfoot?
Yeah, it's unfortunately not as amusing a story as I'd like it to be. Part of it is because there's this culture of assigning silly animal names to Firefox extensions. So Grease Monkey and Platypus and Aardvark and so forth are all in this vein. But the actual name is it's because an earlier version of the system was called Dominoes, because what it does is play with the DOM, the document object model of HTML. And Chickenfoot is a silly animal name which actually is a variant of Dominoes. There's a Chickenfoot variant of Dominoes. So this was this second version of the Dominoes system. Kangaroo is actually much more interesting. They're, if you do a search for my name in Google Images, yeah, here we are in Google Images, the first thing that comes up is not, what, do I have the face detector on? Oh, show all images, yeah. This was before we turned on show all images. So when I was typing my own email address into the system for a while, this is what I was getting. Any other questions?
Thank you.
Okay.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.